Hi, this is John Whitaker for the Mathematical Analysis class, and this is our 17th video lecture. And we left off last time improving equivalencies between three characteristics of sets, and we had to prove one more equivalency, one more implication. So let's remember what that theorem was that we were working on. So it said, if a set E in Rk has one of the following three properties. Then it has the other two. And so here are the three properties. A, E is closed and bounded. B, E is compact. And C, every infinite subset of E has a limit point in E. Okay. We had shown that A implies B and B implies C. What we need to show is that C implies A, and it's a longer part of this proof. Okay, here's the way it goes. So for C to imply A, so what we're assuming is suppose every infinite subset of E has a limit point in E. We want to show E is closed and bound. We're going to show E has these characteristics by really having a contradiction proof. Okay? So we'll start off with suppose E is not bounded. We haven't done a lot with bounded sets, but you might remember what it means to be bounded is there's some real number R, some real number M greater than 0, and a P in E such that the distance between all the points here, well, P doesn't have to be in E, but in the metric space, but the distance between all the points in here and that P will be less than or equal to M. Okay? Okay, so here we're saying E is not bounded. So let's write down what that means. So that means for every m greater than 0, And for every q element of x, there exists a p in E such that the distance between p and q will be greater than m. Okay. So here, let's consider, we're in our K, so let's Q be equal to 0. Then, for m equal to 1, there exists an x sub 1, element of B, such that the norm of x sub 1, that's its distance from 0, is greater than 1. So this is x sub 1, is greater than 1. Okay? And so here we're thinking of this being the norm of x sub 1 minus 0. And that's the distance that x sub 1 is from 0. Is going to be greater than 1. That's what we're thinking. Okay? Okay, so here we next let N2 be an element of J, the math numbers, such that N2 is greater than or equal to the absolute value of x sub 1 plus 1. Then, that's going to act like my new M, the right-hand side. Then there exists an x sub 2 element of E. Well, I'm sorry, this isn't going to be my M, but n sub 2 is going to be my M. Such that the norm of x sub 2 will be greater than or equal to, or just be greater than n sub 2. So we're going to continue this process. So we let n sub 3 be an element of J such that n sub 3 is greater than or equal to the norm of x sub 2 plus 1. Here, I made a mistake, at least in terms of my notation. Let me go back and correct something. Here, right here, this should be the norm of x sub 1. Okay? That's what that should be. Okay. All right, then there exists an x sub 3 element of B such that the norm of x sub 3 will be greater than n sub 3. Continue this pattern to form a sequence x sub n that is a subset of these, an infinite sequence. Okay? And so pictorially, just to give you the idea of the proof of what we're doing in proof, really, if you think in RK, so here's 0, that was our cube, and so that's 0. And then if you think being maybe 1 unit away from 0, we take x1 such that it's bigger than 1 unit away. Maybe this is x1. And then what we do is that we find an x2 that's x1 units away from 0 plus 1. So it's more than that. So maybe x2 is over here. It's distance away from 0. And then x sub 3 is going to be 1 more unit than that away from 0. Maybe it's over here. So that's how we're forming the sequence. So if we think of, we let S be equal to this sequence, then S is infinite. And has no limit points in Rk. Okay? No matter what points you pick in Rk, you can get a neighborhood about it that will not intersect S. And if it doesn't have a limit point in Rk, then it can't have a limit point in E. So S has no limit point in E. Okay? And that's a contradiction because we're assuming every infinite subset of E has a limit point in E. So that means we assumed something wrong, and what we assumed was that E was unbounded, so E must be bounded. All right, now, what if we were trying to also show that E is closed? Well, what if E is not closed? Then, there exists an x sub naught that is an element of Rk that is a limit point of E, but x sub naught is not an element of E. Okay. Then, for n equal to 1, there exists an x sub 1 that's different from x sub naught, that's an element of E, such that x sub 1 minus x sub naught, that norm is less than 1. And that's because that x sub naught is a limit point of E. Okay, so for n equal to 2, there exists an x sub 2, that's an element of E with x sub 2 being different than x sub 1, such that the norm of x sub 2 minus x sub 1 is going to be less than 1/2. To see that such an x sub 2 exists, we look at it this way. If there wasn't such an x of 2, then x of naught could not be a limit point of it. Okay? Because we could look at this neighborhood. Okay, what neighborhood are we going to look at? We're going to look at the neighborhood n sub x of 1 minus x of naught, that's its radius, about x of naught. Okay? This would not contain a point from E different than x of naught. And that'd be a problem because x of naught is supposed to be a limit point of E. Okay. So if that's the neighborhood of x of naught, it's not going to contain x of 1, so it's got to contain something else from E. So that's why that x of 2 has to exist. Okay, we can continue this. So for n equal to 3, there exists x of 3 element B with x of 3 being different than x of 2 and x of 3 being different than x of 1, such that the distance between x of 3 and x of 0 will be less than 1/3. So we continue this process to obtain a set, really a sequence, script S, I'll call it again, of these x of n's. So this S is an infinite set or subset of E, okay, and x of naught is a limit point. Of the script S, or of S, I should say. Okay. Now, here, we let Y be an element of RK. With Y being different than x of naught. Now, note that the distance between x of naught and Y is less than, by a property of the metric, it's less than the distance between x of naught and an x of n, part of the sequence, plus x of n's distance from Y. That's what we have. So that tells us that x sub naught minus y minus the distance between, if you will, x sub n minus x sub naught. So I just pulled this over, and the distance between x sub naught and x sub n is the same thing as the distance between x sub n and x sub naught, is going to be less than or equal to this distance, the distance between x sub n and y. Okay. Now, I'll tell you something bigger than this quantity, at least for many n's. So here, what we get is that this distance minus something bigger than this is 1 over n. It's not for, that's true for all of these types of terms. Okay. Now, so this is less than this, 1 over n. This distance between x sub n and x sub naught is less than 1 over n. So here, this quantity, what I'm writing, is smaller than the quantity above it on the left-hand side because I'm subtracting away something bigger. So that's got to be less than this quantity, this distance. Now, what you do is you pick n big enough that 1 over n is smaller than 1/2 the distance between x sub naught and y. So what I'll write is, we'll have the distance between x sub naught and y minus 1/2 the distance between x sub naught and y is going to be less than or equal to x sub n minus y. And this isn't always true. It's true for n big enough. And so it's going to be true for n big enough. So the only time that it might not be true is for finitely many n. So this happens for all but finitely many n that are natural numbers. Okay? So if we simplify that left-hand side, we just get 1/2 the distance of x sub naught minus y is going to be less than or equal to the distance between x sub n and y for all but finitely many n the natural numbers. And let's say the particular ones are n sub 1, n sub 2, up to n sub j. So what we do is we let r, it's going to be a radius, be equal to the minimum between these numbers. 1/2 of x sub naught, the distance between x sub naught and y. And then x sub n sub 1, distance from y. And then all the way up to x sub n sub j's, distance from y. So there are j plus 1 number of numbers in here. That's fine. Then, here's what we see. The neighborhood with this radius about y will not intersect S except possibly at y. Okay. So what this is showing is that y is not a limit point of S. Okay? Thus, S has no limit points in E. So the only limit point we had of S, I think, was x of naught. Okay? And x of naught was not in S. And so, that contradicts our assumption. That means E must be closed. So that concludes the proof. That C implied A concludes the proof of the theorem. Okay, next I want to prove another theorem. Here's what it says. It's due to Weierstrass, very famous mathematician. What it says is every bounded infinite subset of Rk has a limit point. In Rk. We'll prove this. Okay, so the proof's not so bad. Here's what it says. It says, let E be a bounded subset of Rk. That is infinite. Since E is bounded, by the process that we used to show that A implies B in the previous theorem, what you can show that process implies E is contained in some I, where I is a K cell of Rk. So we know that K cells are compact, so I is compact. Okay. And E would be an infinite subset of I, or of a compact set. So, by a previous theorem, what we know is that E has a limit point in I. And the I is contained in Rk, so E has a limit point in Rk. And that concludes the proof. Okay, next I want to define something. two things, look at examples, and then prove a theorem about these particular topics. So here's a definition. It says two subsets, A and B, of a metric space X are said to be separated if A intersect B equals to the empty set, A intersect B closure. So what's B closure? It's B union its limit points. And A closure intersect B is equal to the empty set. Okay, let's look at some examples. If you have A equal to 0, 1, and B equal to 2, 3, then A and B are separated. And that's easy to see. You can say as A closure is equal to 0 to 1, so you put in the limit points, and B closure is equal to 2 to 3 closed in this way. And so if you take A and intersect it with B closure, you do get the empty set. And if you take A closure, intersect B, you get the empty set there. Some examples. Okay, another definition we want to look at is that a set E is a subset of X where X is a metric space. Is said to be connected if E is not what? Phi is not a union of two non-empty separated sets. So some examples, we think of E being equal to 3 to 8. That is connected. You can't write E as the union of two separated sets. This is my first example. My second example is if you have E equal to 3 to 5 union 7 to 8. That is not connected. as 3 to 5 and 7 to 8 are separated, or two separated sets. And so it is the union of two separated sets. And 3, another maybe clear example, is if you have E is equal to 3 to 5, not including 5, or 3, union 5 to 8, not including 5 to 8, that is not connected. You know, it's missing 5. That's why it's not connected. But it doesn't fit the definition, okay? It can be written down. E can be written down as the union of two separated sets. Namely, these two sets are separated. So here's the last theorem that we're going to do in chapter 2. So this is the last theorem that we'll cover for test 1. And here's what it says. It says a subset E of the real line is connected if and only if it has the following property. If X is an element of E and Y is an element of E, okay, and X is less than some number Z is less than Y, then Z had to be E. Okay, so here we'd like to prove this. It's the if and only if statement. Okay, so we will prove a subset if, this way I should say it, sorry, if E is a connected subset of R, then if X and Y are elements of E with X being less than Z being less than Y, then Z is an element of E. So we're going to prove this direction by proving the contrapositive. Proving the contrapositive. That's what we're going to do. Okay, so what does that mean? We're going to suppose that there's X and Y. There exists X and Y element of E, and X is less than Z is less than Y, but Z is not an element of E. Okay. We want to show that E is not connected. So what we're going to do is we're going to look at these two sets. So let A sub Z be equal to E intersect minus infinity to Z. That set, that's what A is. And B sub Z be equal to the set of E intersect Z to infinity. The first thing we should note is E is equal to the union of A sub Z with B sub Z. And so what we're going to show is that A sub Z and B sub Z are separated. Okay. So since X is an element of A sub Z and Y is an element of B sub Z, then both A sub Z and B sub Z are non-empty. So we're looking about that definition of connectedness, okay? Being connected. Are non-empty. Okay. Since A sub Z is contained in minus infinity to Z, and B sub Z is contained in Z to infinity, then that forces A sub Z and B sub Z to be separate. Hence, E is not connected. So we've proven our theorem. Okay, to show the other direction, again, we're going to prove the contrapositive. So let me write that out. To prove, this is this direction, to prove if X and Y are in E, and X is less than Z is less than Y, then Z is an element of E, implies that E is connected. We will prove that statement. We will prove the contrapositive as an equivalent statement to the statement we have there. Remember, we talked about that in the first video lecture, contrapositive being logically equivalent to a if-then statement. So let E not be connected. Okay? Then, what does that mean? Then there are two non-empty separated sets A and E such that E is equal to A union B. That's what we got. All right, so here's what I'm going to do. we're going to pick an x in A and a y in B. Since x is different than y, they got to be different because they're in separated sets. Okay. We may assume, so they're different, they're real numbers. One of them's got to be bigger than another. So we may assume, without loss of generality, that x is less than y. Okay, now what we're going to do is we're going to define z to be equal to the sup of A intersect x with y, this interval. Then, by a previous theorem, z is an element of the closure of A intersect x with y. All right. Now, as a fact, I might ask you to prove this in the homework later, that if you have A intersect B closure, that's contained in A closure intersect B closure. So this means that Z is in the closure of A intersect XY. That means Z has to be in the closure of A. Now remember, E is separated and equals to A union B. Or E is not connected, and E is equal to A union B. And so A closure has nothing in common with B. So if Z is in A, that means Z cannot be in B. So that means that X is less than or equal to Z is less than 1. So we have two cases to consider. If Z is not an element of A, not an element of A, so either Z is in A or Z is not in A, okay? Then what will happen is X is less than Z, which is less than Y, okay? So that's the type of point we want to be talking about. And Z would not be an element of B. Hey, that's what we want to have happen. Because E is equal to the union of A with B, but Z is not in A and Z is not in B. Okay? In this case. Okay? Z is not in B, but in this case Z isn't in A either. So I want to have one more case to consider. Now, case 2, if Z is an element of A, okay, then we know, Z is not an element of B closure, then there exists a Z sub 1 element of R with Z less than Z sub 1 less than Y, and Z sub 1 is not an element of E. Okay. To see the existence of Z sub 1, suppose for all Z sub 1 in R with Z less than Z sub 1 is less than Y, then Z sub 1 is not, or suppose it was in E. Okay. Note since Z equals to the sup of A intersect X to Y, sup of this set, and Z is less than, Z sub 1 is less than Y, then Z sub 1, Z sub 1 can't be in A. Okay? Now, if Z sub 1 is in B, then for every Z sub 1 with Z being less than Z sub 1 being less than Y, then Z will be an element of B closure, as it would be a limit point. Z would be a limit point. Of B. Okay? And this would contradict, that's a contradiction. What does it contradict? Let me write it out in words. This contradicts A intersect B closure being equal to the empty set. As we're supposing in this case that Z is in A, okay? So we're talking about Z here, okay? So in all cases, we have produced I'll call it Z star. In the first case, it was that sup. In the second case, it was just any point in between the sup and Y. Okay. A Z star such that X is less than Z star, which is less than Y, and Z star is not in E. Okay. And that's what we were looking to do, so that ends the proof. Ladies and gentlemen, that's enough for this video lecture. Thank you very much for your time and patience.